So hello everyone, thanks for joining. Can you please confirm whether you can see my screen and hear my voice?
Yeah, we can hear.
Okay,
Fine.
thanks. And just one reminder, if you write something in chat box, most likely I am not seeing it during the session. So if you want me to see it, just unmute yourself and let me know that you have written something. Then only I can see. So I'll wait for another minute and then we can start. Okay, so I think we can start now. So welcome you all to the second problem solving session for this course titled 5G Wireless Standard Design. And as you are well known that in the second week the key concepts that are being covered is the concept of time in 5G NR framework, and then CRC calculation procedure, transport port block segmentation, a bit overview about LDPC encoding, not too deep. So we'll mostly going to deal on those things. So when I'm talking about 5G NR framework, we hear this term frame. So can one of you tell me what exactly frame represents? Like what it is in context of this 5G NR system design?
A frame has got tens of frames.
True, but let's
And a subframe has got one slot,
okay.
or more than one slot. It really
Okay.
depends upon.
Okay, we'll get to that. Like, we'll go to subframe and slots. But when I'm hearing frame, like, why exactly do we need this frame? We can start from subframe onwards, right? As you say, or maybe slot onwards. Why frame is required?
A slot is a schedulable entity.
Okay. So, what does then the significance of frame? What does it signify?
Multiple user data can be carried out in a frame.
True, but multiple user data can be carried in a slot also. So, why we need frame? Okay, let's first of all, frame is the biggest unit of time in 5G inner framework. It has a fixed duration, that is of, I guess you all know that, 10 millisecond. So your subcarrier spacing may be varying, but it doesn't matter. The frame duration is numerology independent. It's going to be 10 milliseconds. So the significance is as follows. For example, there are certain signals that are only scheduled to be transmitted at every frame. So there is no bigger time slot than frame in the 5G inner framework. That is the biggest one, which always has a fixed duration of 10 millisecond. And as one of you correctly pointed out, each frame is divided into 10 subframe. So subframe is also numerology independent. That means it also has a fixed duration of 1 millisecond. and then comes slot. So where does exactly slot varies uh, than subframe and frames? What is the difference apart from the time duration?
Subcarrier spacing.
Subcarrier
So
spacing
the,
is some.
symbol duration, OFDM symbol duration.
Okay,
TU. Yeah.
correct, but can you be more explicit? I mean, those are the reasons. That's true. That's true. But I'm just saying that where slot varies compared to subframe and frames. Like what exactly separates it out?
A slot has got multiple symbols.
True. How many symbols? With the
There are 14 symbols in a slot. One, four.
So is that 14 always fixed or it can vary based on
No.
subcarrier spacing?
Per slot symbols are fixed 14. Number of slots per subframe will vary depending upon subcarrier space.
Okay, so you are saying that number of symbols in a slot is always fixed. That is 14, right?
It's
So, okay, thanks. So, first difference between frame and subframe and slot is that slot is a dynamic scheduling unit. That is, it's numerology dependent. I mean, frame is always 10 millisecond duration, irrespective of subcarrier spacing. Subframe is always of 1 millisecond duration, but a slot is not. Whenever I want to define a slot duration in terms of time, I need to always look at other system parameters like OFDM symbol duration or subcarrier spacing, because that is going to define it. What is fixed about slot is number of symbols. As you correctly pointed out, there are always 14 symbols, but the duration is not fixed. Duration keeps on varying. For example, for 15 kilohertz subcarrier spacing, let let me write it down here. So frame and subframe are numerology independent. That basically means they are of fixed duration, whereas slot is a dynamic scheduling unit. So for example, let's talk about the slot duration and subframe duration. And another column, let us have subcarrier spacing. So if this is, let's say, 15 kilohertz, your slot duration is going to be 1 millisecond. Your subframe is always 1 millisecond. Now if I make it 60 here, my subframe duration will still remain 1 millisecond, but what is my slot duration is going to be
0.25.
0.25 millisecond, and so on. So this is a good time to ask you, currently we see that the current cellular system, let's say 5G system, are able to serve hundreds onwards user at the same time. So how do you really achieve that? at the same time? How do you do it? How do you schedule? And how often do you schedule?
using PRBs and time slots.
Uh, can you repeat yourself?
Using resource blocks and these exactly slot number, the symbol during number in the slot.
Okay. So is it something related to OFDM time frequency grid?
Yes,
Okay.
yes.
So let us try to draw a kind of diagram. Let's talk about 1, 2, 3, 4 here and 1, 2, 3, 4 here. So this is time and this is frequency. So what is this 1, 2, 3, 4 here? Are those subcarriers here? If I say x-axis is time duration and y-axis is frequency.
It's the PRB numbers, group of 12 carrier frequencies.
No, no, no. This 1, 2, 3, 4 here. These things.
Those are, I mean, like symbol number in the time slot.
Yeah. So this is like first OFDM symbol, and this is like fourth symbol. And what about this one and this three here?
These are PRB numbers.
Okay. Can we break down PRV even more to something more
No,
fundamental?
no, these are of 12 carriers, 12 subcarriers.
Okay. So we're saying these are, let's say, physical resource block PRBs or just RBs. So why don't, okay, so this is so how many users I can schedule in a slot? Like let's say you're okay, I give you some parameters. This is 100 megahertz thing, and let's say 30 kilohertz of spacing. So you will have 3300 subcarriers. So how many users maximum you can schedule in a slot?
So 3300 by 12 into 14.
Okay, 3300 by 12 into
1, 14.
14. Okay, this many numbers you can schedule. But why don't you like why don't we use a single subcarrier? Like why use 12 at a time? Because if I use single subcarrier, then we can schedule much more number of user, right? If I call it X, then I can actually serve 12x number of user if I use one subcarrier instead of concatenating 12 subcarrier at a time and assigning it to a user. Why don't we do that?
It's really depends on channel behavior. Channel might not be available heavily automated or that one atypical subcarrier. So it's better to have a group of subcarriers for which user can get PRB and can use some good number of subcarriers in the PRB.
Okay, okay. Can you just repeat yourself? Like, what is the problem with a large number of subcarriers?
Minimum number of less number of subcarriers in the PRB, right? Let's say one
Yes.
subcarrier per PRB. So the channel might not be available. Channel might be heavily attenuated in that frequency band where the subcarrier is located. So instead, I mean, we can have a large, let's say, sufficiently large number of subcarriers put together and then give it as a resource block to the user. So that user can communicate using some of the subcarriers in the PRB.
Okay. And what I can you point out another maybe important problem if I go for each subcarrier? Uh,
A signaling overhead will be increased.
yeah, like it's like in one slot I am having more than 3k subcarriers, so I have to obtain the channel information corresponds to all of them, so that's a huge overhead. Correct. So based on this discussion, what is the number of slots per frame with 120 kilohertz of subcarrier spacing?
Yeah, it will be 80.
And how we achieve that number?
So like you creating this table, right?
Yes.
So 60 kilohertz 0.25. So 0.25. So in one frame we have in 1 millisecond we can say this four slots. So
Okay.
total in 10 millisecond 40 slots.
Okay.
When we it become 120 kilohertz, so 40 become 80.
Okay. So essentially you are saying if I go for a higher subcarrier spacing of 120 kilohertz here, my slot duration will be something like 0.125 millisecond,
Right.
and subframe duration remains same. So in each subframe I'm going to have 8
8
slots.
slots.
So that translates to 80 in one frame.
Right.
Okay, thanks. Next I would like to
So,
yes.
if sorry to disturb you.
No, no, no,
So, what
please.
will be the answer for your original question? Means why we use frame? Means again, it is not clear.
Okay, the frame. Okay, frame is like the biggest time unit in your 5G NR. So basically there are certain signals. Let's say you are moving from one cell to another, right?
Uh-huh.
So you need to connect to that cell's base station. So those kind of signaling, there are certain signals which are transmitted once in every frame. Like their repetition frequency is every frame, like that.
So, you meant to say that data is transmitted in frame, right? Every frame, not in the subframes, not in the subframe.
Yes, there are
Right? So
certain kind of signals. For example,
yeah.
yeah, for example, when I need to connect to another cell's base station, so
Mm-hmm.
how it basically works, that base station sends this kind of probing signal at certain interval to look for a new user in its coverage area. So when I say that at certain frequency, that frequency it sends, let's say, every frame. So that's its significance. Okay, let me say in this way. Let's say there are certain signals which
Mm-hmm.
are transmitted like every slot. So their frequency, like the repetition frequency is really high, and they are really important. But this kind of probing signal where base station looks for new user in its coverage area, it is not going to transmit at every slot or every symbol, right? Because because these slots are the kind of resources you use for data transmission.
Mm-hmm.
These probing signals are not helping you in that. It's basically eating up the space for another user's data. So you don't want to transmit them like every symbol or every slot. Maybe you're going to transmit them once every frame because you can afford that. If a
Okay.
frame duration is 10 millisecond, it's good enough to look for new user every 10 millisecond. It doesn't make sense to look for user in every microsecond. It's not necessary,
Mm-hmm.
right? Basically these are less important signals which are scheduled in once in every frame. So that's where the concept of frames comes into picture.
Okay.
It's kind of the biggest time unit in the 5G NR framework.
Okay.
So am I able to make you
Yeah.
understand?
Yes. Fine. Thank you. Yeah.
Okay, thank you. So in the next part we have seen three kind of scheduler. Basically you have already seen that slot is a dynamic scheduling unit and base station makes all the decision like which user to serve in every slot and which not to. So what are the three schedulers we have seen in that course? Let's talk with the easiest one, that is first dot. What is that? Okay, first one is the max rate scheduler. Max rate scheduler. So can one of you please clarify why this name and what does it exactly do?
It will schedule the user according to max SNR.
So basically you are saying when it is only going to schedule the user which observe the maximum SNR, right?
Right, right.
And who makes this scheduling decision in a cellular system?
Max scheduler.
True, like I mean like at which end this scheduling decision is implemented, like base station or user?
Base station only.
Base station, correct. See, if I talk another kind of scheduler, that is the round robin one, how it is different from the max rate scheduler? So this scheduler's decision is quite random, right? It really doesn't look at the SNR. It just already make up its mind that okay, this 5 time instant I'm going to serve user 1, or this 5 instant I will serve user 2, irrespective of what their SNR is going to be. So they are kind of serving or scheduling in a round robin format. So what can we say about the pros and cons of this round robin scheduling over max rate scheduler? Can one of you point out maybe a pro and a con?
Pro is that every user will get a chance to transmit.
Okay, okay. Every user will get a chance to transmit or receive. Fine. And what is the uh, downside of that?
Channel utilization. Channel utilization. Channel utilization.
Channel utilization. So when you say channel utilization, can you explain a bit more, like what exactly you mean by that?
If the user is far away and it's quite low, it's scheduled. The base station has to transmit at lower rate.
Okay, okay. So you are saying basically if the user is observing a poor SNR and it is regardless being scheduled or served, the system performance is compromised kind of, right? Or it is not achieving its maximum potential.
Yes, yes.
That's what you want to. Okay, okay. So what is the solution that is being proposed to kind of combine the best of both domain? What scheduler can combine that? Can you remember the name of that scheduler?
Proportional fair.
It's proportional fair.
Proportional fair. Proportional fair. So if I write in terms of math, like the if, but let's say if we are talking about one slot exactly, or one PRB even smaller, then k is the index of user being scheduled. So the way max rate scheduler is going to choose is that it is going to pick the index of the user with maximum rate. For proportional fair, mm, it's almost similar. Apart from that, there's a division by another quantity. So this one is here, instantaneous rate, rate at mth time instant, and this one is here, average rate up to mth instant over a fairness window tau. For detailed calculation you can see the lecture, but I'd like to pose a problem. Let's say I have user 1 here, user 2 here, user 3 here. So user 1 is having instantaneous rate of, let's say, 4.3 bps per hertz. User 2 is having 2.1 bps per hertz, and user 3 is observing, let's say, 0.7 bps per hertz. Here the average rate, and we are talking about second slot. Average rate for user 1 is let's say 2.7, for user 2 it's 1.8, and for user 3 is 0.07. So the round robin scheduler works in this way. It serves the user based on the slot index. Basically, in first slot user 1, second slot user 2, third slot user 3, like that. So if I explicitly talk about the second slot, what is the user max rate scheduler is going to choose for second slot?
User one.
Okay, user 1 max rate scheduler. What is the choice of round robin? Round robin basically serve user based on its index. The slot index and the user index should match. That's the requirement for round robin. So in second slot it's going to serve
User two.
user 2, but user 1 has higher rate, right? Then why it will go for user 2?
Like you said, according to index.
Okay, so it does not really care about the SINR they are observing. It's just random. And what about the proportional pair?
User 3.
User 3, but user 3 is observing the lowest instantaneous rate possible. Why it will go for user 3?
The ratio of both is higher.
Ratio. So intuitively, fine, this is the maths part. Okay, so intuitively, how it explains the working principle of proportional pair? Like, how does it achieve the balance between the max rate scheduler and round robin?
If some user do not get a chance in slot, then its average will go down as the time progresses. And the relative, so depending upon SLR, rate, relative value of this SLR with respect to average will be more, will be higher rate as time progresses. You
Sorry,
might
can
get a
you
chance, you
just
might
a bit louder? I'm not able to hear you.
as time progresses, let's assume that certain user, not even now,
Yeah, yeah, go on.
but as time progresses, let's say certain user do not get chance, it is not
Okay,
scheduled. Its average will go down as time progresses.
correct.
And even though it's the same, even the rate is lower, with respect to this average rate, if the ratio, so relating to average rate, if the ratio is higher, you might get scheduled. Like unemployed, towards unemployed.
So you are saying that if time progresses and a user is not getting a chance for a longer time, but at a certain instant it is observing far higher instantaneous rate compared to its average rate till that instant, it's going to be scheduled, right?
Correct, correct,
Because
yes.
it's going to see much better channel condition than its historic information. That's what is happening, right? So max rate scheduler basically focuses on the maximum SINR. It doesn't really care about other things, being fair or serving all the users. It's going to serve whichever user has the highest rate. Round robin completely ignores the channel condition, whatever SINR user is observing. It has already made up his mind that I am going to serve this user at that time instant. So these two are kind of extreme, too extreme, which are not good in practical scenarios. Proportional fair balances it in this way. First of all, initially you can say that it's maybe act close to max rate scheduling because the user with the stronger channel, since it's observed better SINR, it's going to be served. But if time progresses and if a user is not scheduled, then its average rates also keeps on decreasing. So whenever the at any particular time instant the user's condition, even if it's slightly better, since the denominator is constantly decreasing, that proportional fairness increases. So that particular user, even if it has a lower instantaneous rate compared to others, just because it is not served in previous instant, gives it a better chance of being scheduled at that particular instance. So that's how proportional fair scheduler makes the balance between the max rate scheduler and the round robin counterpart. I hope this point is clear to everyone. If you have any question regarding this, you can ask me. Okay, this is a kind of trivial question for all of you, but it's good to answer. So, which one of the protocol layer responsible for coding and modulation in our 5G NR framework?
Failure.
Physical layer, fine. So, ca- can you point out one of the tasks of Mac layer in that is being taught in the previous week, or we have discussed in the previous session also?
Scheduling is on Mac layer.
Okay, okay. So that intelligent part, right? I mean,
Right.
scheduling decision, whom to schedule, when to schedule. So that is handled by Mac. Okay. So after this, we have seen the. So let me draw this thing. We have file layer at the lowest segment, and we have Mac layer, right? So when Mac layer transmits something to file layer for a particular user, let's say it's transmitting the data for a particular user. So what does it being called in the 5G standard words when I'm transmitting, let's say the Mac, yeah,
Transport block.
transport block. So when a user's data is being transmitted from Mac to file layer, we are calling it transport block. And is there any restriction on the number of transport block you can send per user from Mac to Phi?
Yeah, it is limited to two.
Okay, it's limited to two. So since we are calling this Mac layer as the intelligent one, apart from transmitting data, does it transmit anything else to physical layer? Because physical layer intelligence is kind of limited. Like it needs some information, right? What to do, what kind of things to do. So does Mac layer send anything else?
Yeah, control information also, sir.
Control information. Okay. And why the control information is required?
To get the knowledge of like what is the MCS and how many PRBs you has to use.
Okay. Okay. So saying control information is like MCS and PRB index like this. Fine. So is there any size restriction on transport block, like minimum and maximum? Or we can the transport block can be as low as 1 bit.
It is 24 minimum.
So 24 is minimum, and its corresponding MCS and PRB values are
One PRB and MCS values like 0, so we can use like QPSK.
okay. Okay. And what is the maximum one?
So that we can calculate by multiplying 275 PRB with MCS 27.
275 PRB MCS 27. And MCS 27 is 256 QAM or
256.
256 QAM. So that comes out to be somewhat more than 3 lakhs. So once you have the transport block, what do you do? Like last session we have discussed about this we have some data and we are adding CRC on top of that and feeding it to LDPC encoder and then do modulation and then only we transmit, right? So what is the immediate task of file layer after receiving one transport block?
CRC check.
uh, okay, I'm talking about like transmitter side. So
CRC insertion, yes. Then
okay, CRC insertion, fine. Is there any fixed number that's standard defined?
16 or 24.
CRC insertion happens 16 or 24 bits. Fine. And what is the function of CRC here? Like it does error correction, error detection, or both, something like that.
It will detect error.
It will detect error. Okay. So if let's say hypothetical situation, I have a 24-bit CRC, and let's say in the when the information is transmitted to receiver side, I have a burst error of 34 bits, single burst error. So will since we have already this CRC insertion, it will be detected at the receiver end, right?
Right.
Are, are you sure? Because it's a 24-bit CRC we have done, and I'm saying that there is a single burst error of 34 bits. Can it?
34-bit, it is not possible.
It cannot do. So how, like, what is the maximum limit it can detect error?
That I'm not sure.
Okay. So actually,
24.
okay. So actually, yeah, correct. So for n-bit CRC, it can detect the error at max n. Of course, it can detect the error if the it's less than n bit, but maximum it can n bit. Once it goes over n bit, it won't be able to. So how does it exactly CRC insertion happen? If I go into the mathematics part, how this procedure is really happening? Like this okay, this transport block we receive, that's a string of binary numbers, right? So how exactly we achieve CRC insertion?
We take a polynomial.
Okay, and what is it called, this polynomial thing? It's a generator polynomial, right?
Yeah.
Generator polynomial. So this CRC append block basically treating this transport block as a string of binary number, and it's employing a generator polynomial. By the way, this generator polynomial knowledge, does the receiver have it?
Yes.
And why it's necessary for the receiver to be aware of the exact generator polynomial being used at the transmitter end?
It should decode CRC.
Okay, it should decode CRC. Fine. So in a standards language, you have, let's say, hypothetical situation, you have a 16-bit transport block, even if it doesn't exist because the minimum size is 24, but just for a hands-on math, we are considering a 16-bit transport block and generator polynomial written in this way. So what does it exactly signify that d to the power 4 d cube plus 1? What is that? So if we talk about having a polynomial of degree 4 here, so you pick the length of CRC is equal to the degree of polynomial, that is basically corresponds to d to the power you will write it in this way, d to the power 4 plus d cube plus 0 into d square plus 0 into d plus 1. So you have d to the power 4 in your expression, so you'll have 1 here, 3 also you'll have 1, the coefficient corresponding to d square is 0, so you'll have 0, coefficient corresponds to d is 0, again 0, 1 is 1. So your CRC is actually this. So we have our transport block given, we have our CRC given. So what is the procedure of calculating CRC here for this particular transport block?
Division.
Division. So I should divide this whole thing by this one, right?
Yes.
Let's write it down, 11001, 110101110, 1011110. So I'll have 11001 here. So when I say division here, what operation I need to do here? Like AND or XNOR, XOR,
XOR operation.
XOR operation. So what I am getting from here, 0 and 1.
1.
Next also 1. This one here, 0 0.
All are zeros.
All are 0. So we are kind of ignoring them.
Yeah.
So how many bits we need to bring down here?
3.
3. So all are 1. So I'm not really worrying about this part because CRC is the reminder, right, of this division. Again this, so I have 0 here, 1 here, 1 here. These two are 0, so I'm kind of ignoring them. Now I need 2 zeros. One, 0. Okay, all 4 them are going to be 0. So here I need 4 bits. Zero here, 1 here, again 0, all zeros. So 0, 0, here.
I have to return to append 4 zeros and carry out division. Prior to division, you need to append zeros and then carry out
Okay,
division.
I need to append zeros. How many I need to append here?
4.
4 zeros. Okay, let me extend here. So here I had 4 here, another 2 came here. Fine, I'm left with 3 zeros and I'm getting 1 1 0 1 0. So what is the reminder I have now after performing this division? By the way, the dividend here is I'm getting wrong. Here there should be 1 0 included here, but we do not really care about that because not part of CRC. So this is what I am having as a reminder. So this is going to be my CRC. And I am going to append this after the transport block. And the receiver side, what is the procedure?
The window should be 0. With this appended CS.
Can you a bit louder? I'm not
So
able.
with this appended CRC, you carry out division, remainder should be 0.
Okay, so assuming that I have received this entire like 16-bit transport block plus appended 4-bit CRC, that is this 20-bit string, that is no error. I received as it is. If the receiver divide by this polynomial again, the remainder will come out to be all zeros. And what if remainder is non-zero? What will
So
happen?
Error is there. Error is there.
Error is there. So in that case, what will happen?
CRC will change.
ARQ, ARQ or HRQ?
CRC won't
Repeat,
change actually.
repeat.
Yeah, one of
It will
you
repeat,
correctly saying what will happen?
it will repeat the transmission depending upon the scheme. Yes, combining or
Yep.
intermittent redundancy.
So basically, it will send a knack, not acknowledging that is the transmission is not successful. And as you currently pointed out, that hybrid ARQ version, whether it's just combining or incremental redundancy, it will send the next version of that. So this HARQ, by the way, is that happening in the file layer?
Not clear, not clear.
So where is that exactly implemented? HARQ?
At MAC layer.
Mac layer. Okay. So it's like Mac layer is the intelligent one which is making all the decisions. So what happens? Like, okay, let me introduce a new slide here. So we have now our transport block whose size can vary from 24 onwards some 3 lakhs. I don't remember the exact value here. So we have added CRC. Fine. So what is the next step? Where should these things go? In a transmission chain, of course, I'm asking.
LDPC.
Okay, LDPC encoder. Fine. So is that any pre-processing needed before I send the entire thing to LDPC encoder, or I can just feed the raw value of the whatever the transport block size is? Let's say I have a transport block of size something like 1.5 lakhs bits, transport block plus CRC. So I can submit it at one go, right, as a one block.
The fragmentation happens.
Uh, Sorry,
The fragmentation. Transport
fragmentation.
block is
Okay, so you are saying basically I need to break it down. Why exactly I need to break it down?
the maximum code works in 8448. So we have to break it down.
Maximum code word that can LTPC encoder take is 8448. Fine, but why is that so? Like, why we need that? Or like, let's say pose the question in this way: why the standard fix uh, a number as small as 8.8448, where we can just feed whatever we have transport block size at one go? Let's say 1.5 lakh. What is the issue while feeding this 1.5 lakh at a time bits?
So on the complexity of LDPC encoder, fixed generator matrices G matrix.
Okay, okay. So yeah, that's true. It is there in standard, but it is because they are, because of the, first of all, we'll have a huge implementation complexity. It's true. It's of course true. There is a base graph and there is parity check matrix of fixed sizes and all that. That's true, but those are, they are in the first place because we cannot feed any arbitrarily large block of data, and that is because of the high encoding complexity, both encoding and decoding complexity also. because if you have to process 1.5 lakhs bits at a go, the implementation, I'm talking about the hardware implementation part with FPGA and all, the complexity would be huge, and even it may not be possible to do that. And there is another benefit also in breaking it into small chunks. What is that? Um, so first of all, we can break it down, that's okay, to reduce the complexity. That is one thing, fine. And what is another benefit of breaking it down into chunks?
Maybe error correction capacity, forward error correction might happen quickly or reliably. FEC happens, might happen reliably with smaller code block size.
Okay. um, Not exactly, because when I say like actually, if your code block size increases, you can decode your information with lower SNR, right? So that is not exactly the reason. Actually, we have the facility of parallel encoding and decoding when I break it down into small chunks. Instead of having a one circuit with an enormous complexity for processing arbitrarily large code block, we can have a fixed number, let's say what is defined in standard 8448, and we can have multiple encoder and parallel sorry, we have multiple encoder and decoders that are working parallel. So in that way, the efficiency also increases. But what is the issue when you break it down into chunks?
There are restricted number of sizes because of which we need 12 billion bits.
So you are saying the restricted number, that is the 8448, that is saying, right?
No, not you're even below restrict 8448. There are, I mean, discrete set of numbers which are feasible for them.
Okay,
It's not all continuous.
okay. And why is that discrete number required?
Because we need not, there's a base graph matrix available from which we generate generator matrix or parity check matrix.
Okay, okay. So we have not actually gone there, but thanks for it. So what I'm basically trying to point out here is that whenever you are segmenting your transport block, you need to introduce additional redundancy, right? So let me write it down here. Maximum code block size 8448 is not entirely true, but okay, as of now we consider it 8448. So I'm having a code block of 8448. So do I need CRC on top of that for it?
Yes, the CBCRC and TBCRC.
Okay, so I need CRC here also. So the scenario is something like that. I have transport block per CRC. If this thing is more than 8448, I'm going to break it down into at least two and possibly more code blocks. Where I will have CRC here also. So what is the uh, usefulness having these CRCs, which you said these are called CBCRCs? Okay, why do we need them? We already have this 3BCRC, right? So why should we even go for CBCRC?
Only that particular CBC code block can be transferred, not entire transport block. If the MAC layer can detect error in code blocks, it can retransmit only that block.
Okay, so you are saying basically if I have this additional CRCs for every code block, and if the error is in only one code block and not in the others, then if I had not this CRB CRCs, I have to retransmit the whole transmit block, transport block. But now since I can know that which code block has errors, I can request for only retransmission of that particular code block. Is that what you are referring to, right?
Yes, yes.
Okay. So what purpose does it serve? I mean, what additional advantage we have for that?
It's increased channel utilization. Need not retransmit something.
Okay, so it will like the reduces the redundancy. That's what you are pointing out, increasing the efficiency, because every bit is kind of a resource, and when you are saving a large, like when you are need not retransmit a large chunk of data, you are basically saving the resources, and as you said, the channel utilization is improving. Okay, fine. That is one nice benefit. And what is the additional benefit on top of that, having those CRCs and all, CBCRCs and 3BCRCs? Are those always going to be generated using same generator polynomial or
There are different polynomials.
different polynomials? And what is the benefit we can achieve from there?
So if something is fixed in TBCRC, it can be caught in CBCRC and vice versa.
Okay, so it's like security implementation at different level. If one CRC check, like let's say in TBCRC level, the potential errors goes through, it might be caught in CBCRC. That's what you are pointing out.
Yes, yes.
Okay, so let's pick a arbitrary number. Let's say something like 19K is my transmit block size, and this is the maximum input code block size. So I'm not getting into the detailed math as of now. So how many code block you think I'll require here if I have 19K transmit block size and the maximum size is 8448, of course? So how many code blocks you think I will need?
Three.
3. Okay, I'll need 3 code blocks. So as of now, what I see, my immediate understanding is I can fill first two code blocks with maximum number of bits, 8448, 8448, and the second one will be left with somewhat, let's say, 2.5K. This is the first code block. No, this is the second. This is the first. This is second. This is the third code block. Only have 2.5K bits. Um, so is that the way it is done in standard?
No, no.
So what is the issue with this kind of thing? Because I am actually kind of utilizing it to the max for first two code blocks at least. So what is the issue with this kind of segmentation?
Different sizes should not be there.
Okay, but what is the problem if there been this kind of thing? Like, okay, that's one thing, that it's not implemented in standard, that I understand. But I'm just trying to see here why this will what issues this kind of segmentation will possibly create. That's what I'm trying to see here.
We
Okay,
all might require different generator matrix or parity check matrix to generate LDPC.
okay, but that should not
At least the
create a
last
issue.
one. At least the last one.
Okay, but that should not create a issue, right? Especially, okay, for my side, I'll give this argument that, see, for first two code blocks I have 8448 number of bits, so it's the maximum code block size, and we know that if the code block size increases, my decoding will be become easier because I can decode it over low SNR. So that's my argument from my end. So why not fill first two code block with the maximum bits and leave the third one with whatever is remaining. Actually, if I, yeah, you're saying something.
For third block, higher SNR will be required for decoding.
For third block, higher SNR will be required. Why is that? Because you are saying that block error
The
rate
size,
increases for lower number of code block size. So is that what you are
yes.
pointing out? Okay. And what is the issue with that? Let's say for all of them the SNR level is same, S1, S1, S1. S1 is able to, with S1 SNR we are able to decode the information in the first and second code block correctly, but S1 may not be sufficient for the third one. That's what you have pointed out. So we'll encounter error. So what is the issue with that?
Decoder performance will be impacted.
Okay, true, but how is so? Like, can you go in more detail, like explicitly, like what issue I am going to have with that? Okay, let's pick your words only. You are saying that decoder performance will get impacted. So, okay, I would be able to decode the first and second code block, but the third code block I'll fail. What will happen then? You'll ask for retransmission, right? As per our understanding from the previous session.
Yes.
Yes.
And as long as this third code block is not cleared, my entire transport block is stuck. So is that correct what I'm saying?
Correct.
Because your third,
Correct.
so essentially
Yes.
it's like a chain where the uh, chain is as strong as its weakest component. So here the entire transport block will be defined in terms of its the third code block, which is the weakest one. So as long as third is not cleared, the entire transport block is kind of stuck. So I have to keep asking for retransmission. So essentially that is the issue. So
Can you elaborate this low SNR for higher code blocks? This is challenging to understand. What is that?
okay, you are asking for again,
For higher code block size, we require low SNR.
yes.
Can you elaborate that?
So when your code block size increases, your for decoding the information you can decode under even low SNR. For example, if my code block size is 8448, I can decode it maybe under a SNR of 0 dB, a hypothetical number. But in the same place, if my code block length reduces, like let's say now 200 yeah, 2000 something, then the 0 dB SNR may not be sufficient for the decoding.
Why is that so? Why is that so?
Okay, why is that so?
Because channel is going to be the same, the
Yes,
PRP and everything is going to be same. So how does it matter?
that I need to really check. As of now, I don't know really, but is it something related to coherent integration? Like if I have a longer, I'm just guessing just. but I don't really know the answer as of
The
now.
professor also hurriedly told that I will run ahead.
Okay, okay. Actually, I need to get back to the basics and check why exactly. That's a nice question, but I am not able to answer as of now. I need to check it. Maybe in the next session, I will like I
That's
can
fine.
answer that.
Yes, that's fine.
So, what is the solution here? We should go for then for a uneven segmentation is not going to work because the weak it is always going to be defined by or stuck by the weakest one's performance. So, what is the way out in standard?
So users should be same.
Okay, so the code block length is all the code block size should be same so that they don't get stuck by the weakest one's performance, right?
Yes.
Correct. So let us introduce another slide here. So I'll now would like to briefly talk about LDPC encoding. So how is that encoding happen in terms of, let's say, math? Like, I am sure you must have seen it. What are the ingredients? Like, basically what we need.
I will check my case.
Okay, we need one parity check matrix. It's defined as H. Fine. And how does this matrix relates to the code word, valid code word?
M into H transpose. Message bits into H transpose. Message block into H transpose. Is the code word.
So
Message message word into H transpose.
uh,
Am I audible?
I am not able to. Can you just
I'm audible. The message block, the message vector into H transpose.
okay, message vector into H transpose. Let's talk it about M H transpose. So what does that mean? Like what it's going to do?
This vector into matrix multiplication is going to generate one more word, which is the encoded word.
Okay. So for a valid code word, if I call this valid code word X, this property it should satisfy from lecture, right? Hx is equal to 0, or X should be in the null space of parity matrix.
Yes.
But my question is, like, H dimension of H is huge, right? Even if you have a input code block size of 8448. So how are you going to manage that? You can certainly not store your H for every possible transport block size, right?
Yes.
Because you have very limited memory. So what is your way out here?
The base graph matrix.
Okay,
It
fine. You
generate
have a base
H.
graph matrix. And this is part one that you always have. And what is the second thing?
And the size of identity matrix. ZC, I think. Size of identity matrix.
Okay. And that has a particular name. It's a lifting size, right? That's what you are
Lifting
referring
size.
to.
Yeah, lifting size.
Lifting size. So you are saying you can actually combine these two both and get any H you need, right?
Yes, yes, yes.
And this lifting size, can this be continuous? Like any possible number, or there are some restricted ones only?
There are restrictions. Restrictions. The
There
matrix,
are
there is a table
restrictions.
available. There are a local
Okay.
table available.
So how does this base graph and this identity matrix of lifting size works? Just I'm trying to understand. Let's say base graph has certain numbers like A11, let's say A12, A21, and A22. These are certain values. So how I am supposed to construct a H from this? Let's say I am given a lifting size of 2 as of now, some arbitrary number. So how should these values are going to affect the identity matrix to create the parity check matrix H?
The every identity matrix is replaced by this what shuffling of columns as per A11 or as per A21.
Shuffling of columns. Okay. Let's say if I choose A11 as 0, so what change it will do to the identity matrix?
No shuffling as it is.
No change. Okay. And if I let's say make it 1,
It is, I mean, it is cyclically shifted to second by one position. The
okay.
first column is cyclically shifted by one position.
Okay. So you are saying that based on the values in the index in base graph matrix, we have to modify, like basically circularly shift the identity matrix of lifting size accordingly, and then we'll get our parity check matrix. So in that way I need to only store the base graph matrix, which is of a very small dimension, that we can store in the limited memory, and identity matrix we need not anyway save. We need to store the only the lifting sizes, and from this scalar and this matrix we can generate some discrete size of parity check matrix, right?
Yes, yes, yes.
Okay. So in the 5G NR standard, this how many base graphs are there? Like anything like 1, 2, 3, 4, or one only? Like when LDPC encoding is defined in standard, is there only a single base graph possible? Like for example, your requirements can hugely vary, right? Let's say if you are talking about transmission of an email or something, you and a low SNR condition, then you will have very lower data rate and also low code rate also. And if you go for something like video or like that in a high SNR condition, you are going to observe higher data rate and higher code rates. So in LDPC encoding, are all these accommodated using a single base graph matrix, or it requires more than one?
We have two base graphs.
Two base graphs, okay. And what is the difference between them? Like they are catering to some different environments or different requirements, something like that.
Base graph 1 is used for higher code rates,
Okay.
whereas 2 is used for lower code rates.
Okay. So this 8448 maximum input code block size, that applies to base graph 1 or base graph 2?
Base graph 1.
Base graph 1. And what is the limit for base graph 2? Some number, right? It's more than 8448 or less than that?
Less than.
Less than that. Okay, it's like 3840 or something. Fine. Um, what is the minimum code rate possible in base graph 1? Okay, what is the maximum? Anyone? Since it caters to higher SNR condition and high code rate, it should get very
It's
close to
7
1.
byte. I think 7 byte.
Okay,
7 byte.
I guess 8 by 9 most likely. I'm not sure. I need to check once, but most likely it's 8 by 9. And what is the minimum it requires code rate?
1 byte or 1 byte.
Uh, uh, Actually, for base graph 1, it's 1 by 3 because it's designed for moderate to higher code rate, so it's okay with that. But what is the minimum code rate for base graph 2? Minimum is actually 1 by 5 for base graph 2.
Okay.
So whenever the input code block uh, fed to LDPC encoder, it always arrange it into systematic columns, right? So irrespective of the number of code blocks, the number of systematic columns, is it fixed or is it varying? Let's talk about base graph 1. It applies to base graph 2 also, but as of now you can talk about base graph 1. So whatever
It is
input,
fixed number.
okay, it's a fixed number. So since we are talking about systematic columns, you are saying the number of column is fixed. So is the number of rows fixed also? Okay, number of rows cannot be fixed, right? Because your input code block length can be a variable size. Its maximum value is 8448 for base graph 1. So we can fix the number of columns, that's okay, which is 22 for base graph 1. But the number of bits per row is going to vary, because then only you can accommodate varying size of input code blocks. So with that we can handle this question here. So it says that in our system with standard 100 megahertz bandwidth and some subcarrier spacing, so user is allocated a transport block size of 14010 bits. It's asked to consider the LDPC encoder with base graph 1, and you refer to the lifting size table, and we have to calculate the code block size for transport block. Okay, so how do I proceed in this scenario? Like what checks I need to perform first of all? So I have a transport block size of 14010. So what is the CRC I need to append to it, like the number of bits?
Does it include CRC 14010?
uh, Sorry, I cannot hear
Does
you.
it include this 24?
Okay, I have to
14010.
plus 24-bit CRC I need to append, right?
Does it include 14010 given? Does it include 24 or not?
Okay, no, 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 it doesn't, because it's the transport block that is being transferred from Mac to file layer. CRC insertion we need to do in the file layer, so it's not included.
TB plus CRC, I think that has been partitioned. Entire TB and TB CRC. TB plus TB CRC is fragmented.
Um, Sorry, can you repeat once?
And the TB, the transport block contains TBCRC also.
Uh, but TVCRC part we need to add in the physical layer itself. Na? I mean, when it says that user is allocated a transport block, this 14010 doesn't contain the CRC, right? Because once we receive the transport block, then we add CRC on top of that. Or I'm getting wrong here.
No,
Uh,
no, it's CBCRC. CBCRC is added in the
okay, okay, yes, yes,
physical.
definitely, yes, yes. That we will go, but first we need to check whether okay, let's say why we need CBCRs in the first place. Like if my transport block size is less than the maximum input block size, is CBCRs is also included in that scenario or
No, no.
not? So it's required when the it's segmented, right?
Yeah.
So it's okay, it's going to be segmented because of this is greater than 8448. Now I'm sure there is going to be more than one code blocks. Then I need CBCRC. Fine. So this transport block plus CRC, this number is 14034. So what is the formula to calculate number of code blocks? Let's say there is a C number of code blocks. How should I get that? I need to divide this entire payload thing here, like transport block plus CRC. We divide it by 8448, but we have to also account for, as you pointed out, for CBCRC. So we need to make the room for it. So we subtract 24. So we can get here integer or we can get here some fractional integer. So we need to floor it. So this is going to result into two code blocks. And what is the total payload after adding CBCRC on top of it? Let's call it B dash. So how do you obtain this value? It's the transport block plus TBCRC thing, that is 14034 plus
C224.
we have C code blocks. In each code blocks we need to have 24-bit CRC. So it's C cross 24. Correct. So it's like 14034 plus 2 into 24, that is 48. So it essentially becomes 14082. Okay, this is the number I get. But what should be the code block size for me here? How should I get that? Should I just divide it by 2? 14082 divided by 2 comes out to be 7041. So is that my code block size going to be that I am going to feed to LDPC encoder, or it need to be some pre-processing is required?
A smallest number greater than 7041 based on this upper table.
Smallest number greater than, okay. So you are saying that I'm supposed to have k dash, which should be greater than 7041 or less than 7041?
Greater than 70.
Greater than 7041, fine. And this k dash here has some formula,
Yes, 22, I think 22 multiplied by this number. Should be
like there
given,
is
right?
the number of columns is already fixed. So as you mentioned,
Yeah.
that is 22 times some number, right? ZC. And what is ZC here? The lifting size. So let us it's 22 and this is 7041, so let's try with 320 here. So 320 times 22, it's 7040, but it's less than 7041, so 320 cannot be lifting size, it should be more than 320. Immediate next to 320 is 384 and 352, so 352 is the immediate next to 320. So if I do 352, it comes out to be 7744. If I put ZC 352, this comes out to be 7744. So this is the input code block size that I am going to feed to LDPC encoder. So what about this? We have this useful information 7041 bits, but the LDPC encoder input should be 7744. So there are redundant bits. How many? 7041, so 703. So these bits has any name, this redundant bits?
These are filler bits.
These are filler bits, so basically they don't carry any useful information. Their purpose is only to uh, make the LDPC encoders in input code block size uh, given in the standards. That's the purpose. So here my code block size length is going to be 7744, right?
Yes, yes.
So next question is a kind of extension of that only. So basically ask about the number of filler bits per code block. So we have already calculated there are 703 redundant bits per code block. So third one is the answer. About the lifting size, that also we have seen, it's 352. Okay, so what is the LDPC encoder output length for the TV given in the previous question? So how do I get here? Remember the question asked that about base graph 1. So what is the output length is going to be? Base graph 1. What is the mother code rate for base graph 1? Mother code rate basically means the code rate at which LDPC encoder encodes the code word.
1/3.
So mother code rate is 1 by 3. So can this help me to get the output code block length for the question? Okay, what is the input code block size?
Three times of 7744.
Okay, output code block length is 3 times 7744. It's 2 1 3 4 3 1 3 2 Two three two three two. So second one is the answer. Now assume instead of base graph 1, if the question asks you about base graph 2, will your answer remain same? What is the LDPC encoder output length? Output code block length. The same question, I'm just saying that I'm going to implement base graph 2 because my SNR reduces.
Depends on mother code rate. How much is it?
Okay, depends on mother code rate. So what is the mother code rate for base graph 2? Okay, is it going to be
But
more or less? Compared to base graph 1, the mother code rate of base graph 2, is that going to be more or is that going to be less? Okay, if I compare the scenario, base graph 1 is for uh, scenarios when you have better channel condition, when you are using higher code rate. This is where this is what base graph 1 stands for, whereas base graph 2 stands for the worst conditions like bad
obviously
SNR.
less. It's a bad SNR, less.
So it's going to be less. And why exactly we need uh, lesser code rate here?
More, we want more redundant bits so that we can carry out FPC.
Okay. So basically you want your encoding to be more robust. That's what you are referring to, right? In worse channel
Yeah.
conditions. So actually the mother code rate in base graph 2 is 1 over 5. So should I now uh,
5 times. 5 times.
there is a catch here. It's not going to be 5 times 7744. Can you point out why?
So the block size will vary with motherboard base graph 2. The block length may vary with base graph 2.
Correct. For base graph 2, your maximum input code block length is not 8448 anymore. For base graph 2, it can only be 3840. So I just cannot multiply. It's 5 times 7744. Even if my transport block size remain the same, now the number of code blocks is going to increase because the maximum code block length the LDPC encoder while implementing base graph 2 can accommodate is only 3840. So accordingly it will change. So it just cannot multiply 5 times 7444 here. So this can be a good exercise for base graph 2. So the question kind of continues in context of the previous one. It's trivial only. So to answer this question, that what is the best approach to maintain a link when user experiences sudden drop in SNR? It's not really related to the content of week 2. I'm just keeping it as a revision for the overall content. So when the user experiences a sudden drop in SNR, what is the best approach to maintain a link? Should we modify the CRC polynomial or we do something else, increase transport block CRC length?
Decrease code rate.
You have to decrease code rate because that is the most fundamental thing. That's the only way we can make it more robust.
One question is where the inner bits are removed. and which block is responsible, or which layer is responsible to remove the filler bits. Hello.
Hello.
Which block is responsible to remove filler bits?
Which block is responsible to?
To remove, or which layer is responsible to remove filler bits?
Okay, which block is responsible for removal of filler bits?
But after LDPC decoding, we don't require filler bits if everything is correct.
Uh, yes, true.
Prior to LDPC encoding, filler bits are added. We have LDPC encoding and then modulation, transmission, and central frequency and frequency shifting, transmission, demodulation, LDPC decoding. And now the things filler bits can be removed, right?
Yes. So filler bits is removed by
Physical layer or MAC layer,
uh,
or along with filler bits, everything is sent out and then MAC checks. Yes, yes.
so we are asking at what stage the filler bit is removed, right?
Physically.
It should be removed in the physical layer. I'm just trying to remember at which block is going to remove it, because
After LDPC decoding, those are no longer required, right?
yes,
Those are,
definitely, definitely.
so along with filler bits, everything is sent to MAC layer, or those are removed and sent to MAC layer for further error correction, for error detection, I think.
Actually, in third week's content, more intermediate blocks will be introduced, like red matching or something. But I don't exactly remember which block is going to remove the filler bit. I also need to study that. It is going to be in physical layer only, but as of now, I am unable to point out the exact block which is responsible for removal of filler bits. It's is it
I
red
think they are
matching?
removed during the LDPC.
Okay, LDPC
De-
decoder
uh,
itself, you are saying.
for LDPC decoder, we require it. LDPC decoder will decode everything because after filler bits, LDPC encoder will work on the message vector, right? And will
Yes,
generate
so
code.
whenever, like, yeah, like when it will be passed through LDPC decoding, the filler bit should be there. It would be only, it can be only removed afterwards. Yes.
Correct.
Yes, during the desegmentation of all the blocks.
So at which layer? Physical layer or MAC layer? Along with filler
It's at
bits, things are
physical.
along with filler bits, things are sent to MAC layer.
No, no, no. I think you remove everything in the physical, and what goes up would be
So
only bits
the
without.
fragmentation happens at which layer?
I think it is still at physical layer.
Or MAC layer? Fragmentation happens at MAC layer. HARQ and fragmentation, defragmentation happens at MAC layer, right?
Fragmentation happens in the radio link layer, right? I mean the one
Why
above
did you?
Mac one.
The transport block is the entity at MAC layer, right? Transport block is the entity at MAC layer.
Mm-hmm. True.
So why did you leave there?
Okay, I need to study that, and then only I can answer that.
Okay. Because it says rate matching block. Once again, Chat GPT says rate matching block.
Actually, this rate matching thing
It's
will
not
be
introduced in the second week. Not
it,
introduced in the
it
second
it
week.
is
Yeah.
coming in the third week. But what I can vaguely remember that LDPC encoder encodes in the mother rate, that is one third, but the rate requirement is going to be different for different scenario, and rate matching layer kind of perform that. So, but true, I need to check that which layer is exactly
So
responsible for
anyway,
removal of
anyway,
rate.
third week is available. Third week is available.
Okay, okay, third week is available already. Okay,
Yes, already. You can go through.
then I need to study and then I'll be able to
Yes.
know that. Yeah. So, in case there is any more questions, I'm happy to take. I'll try to answer it, or otherwise I'll conclude the session. Thank you all for being with me for the entire session.
Thanks.
Thank you, thank you,
Thank you.
thank you all, thank you. So I need to next time I need to know that which block is responsible for the filler bit, and there is another question which I was not able to answer. What is that?
The block size and SNR relation.
True, true,
SNR and
true,
block
true,
size.
true. Like, yeah, now I remember that why higher code block size will help and decoding of signal under low SNR condition. Thanks.
So why low SNR suffice for higher block size?
I will get back with the answers for these two questions in the next session.
Please, thank you. Yeah.
Yeah, thank you. So I'm concluding this session.